Welcome to Calculus. Today we will investigate finding velocity and acceleration functions given a position function. We'll take a look at one example. Our first example is about a particle that moves along a horizontal line. We're given a position function s of t, so for our example that's negative t squared plus 8t plus 65 for times greater than 0 or equal to 0. And we want to do four things. We want to start off by finding two different functions based on the position function. We want to find the velocity function. We want to find the acceleration function. So let's do that first. There's a real basic relationship between position, velocity, and acceleration. And basically it boils down to rates of change. So if we think about how velocity is related to position, velocity is the rate of change of the position over time. A lot of times we think miles per hour. Again, it's a rate of change based on position. Well, that's nothing but the derivative. So as we start with this first example, if I've got a position function, I'll record down here as well, s of t equals negative t squared plus 8t plus 65. If I want to find the velocity function, I simply need to take the derivative of the position function. And I can say that here just with that notation to say velocity equals the derivative of position. And so for us, that would be applying our derivative rules for polynomials, negative 2t plus 8. And we can see because it is a quadratic function to begin with, our velocity function is a linear function. The relationship that follows with acceleration is similar to the relationship between velocity and position. Acceleration is simply the derivative of the velocity function, because what acceleration describes is the rate of change of velocity according to time. So what it amounts to is just taking derivative of negative 2t plus 8, that linear function, and that's simply negative 2. So our acceleration function turns out to be just constant. And in fact, for this scenario, we would say the acceleration is a constant value. It's negative 2. So once I've found those functions, that's parts A and B, I want to find the times t when the particle changes directions and the intervals of time when the particle is moving left and moving right. So probably to help us, we ought to actually move to part D first so that we can see the graphs of these three functions, the position, the acceleration, velocity, and acceleration. So let's graph our functions first, and then we'll find that we can answer these questions about change of direction and also moving left or moving right. So we'll start off with the position function. That's negative t squared plus 8t plus 65. And let's create a table for that. So time is our independent variable, and we are restricting it to 0 or positive values. So we'll go 0, 1, 2, 3, 4, and 5. Perhaps we'll need more, we'll see. And we're going to graph s of t. So for our first value there, it's going to be 0.65. I see if I plug in 0 for my time, my first two terms will disappear. For my second value here, I'm going to plug in negative positive 1. So negative 1 squared plus 8 times 1 plus 65. So that's going to be negative 1 plus 8, that's 7, plus 65 is going to give us a value of 65 plus 7, 72. Keep on going. At positive 2. That's negative 2 squared plus a times 2 plus 65. So we'll write that sum here. That's negative 4 plus 16. So that would amount to 12 plus 65. And that's going to give us 77. Calculate with 3. Negative 3 squared plus 8 times 3 plus 65 is negative 9 plus 24 plus 65. And that's going to be negative 15 plus 65. I'm sorry, 15 plus 65, which will be 80. And then at 4, negative 4 squared plus a times 4 plus 65. So that'll be negative 16 plus 32, which is going to be 16 plus 65. And that's going to be 81. And then at 5, negative 5 squared plus 8 times 5 plus 65. And that would give us negative 25 plus 40. So that's going to be 15 plus 65 is 80. So we located our vertex there at 481. And we could extrapolate that probably if we went up forward 6 and 7, our values should be symmetric, so 77 and 72. Well, let's graph here. Notice that my x-axis, my horizontal axis is time, and it's by ones. My vertical axis is distance or position on this horizontal line that our particle is moving on, and it's by 50s. So I got to scale that way. So 0.65 is just estimating about there. 172 is a little higher. 380. I'm sorry, that's 277. We'll estimate that 380 is a little higher. 481, that's our vertex. And then 580, 677. So here we see a symmetric fall down, and 772. So back to 72. And so our parabola, if we sketch, it's definitely opening downward, has a shape roughly as so. And so as we think about what this would mean in terms of an object moving along a horizontal line, if I have this horizontal line here, and that's marked with some distances, let's just say 20, 40, 60, 80, 100. As I were to track a particle at time 0, it would be at 65, so just roughly here. And then as I go, the particle is going to head in this direction to the right towards 81. And then at that point, that's about 4 seconds into the movement here, it's going to change directions and head back to the left. And then the particle will continue moving until it crosses past 0 onto a negative side of this horizontal line, and it would continue in that direction if the experiment were prolonged forever. So the position function really gives some insight into how the particle's moving over time. And that'll help us as we go to part C, but let's keep graphing here. I also want to graph the velocity function. So that's a little simpler. That's this negative 2t plus 8. So the way we would graph that function is really by finding the y-intercept. That's 8. Then it's going to go down by 2 every 1. So if I go over to 1, it's going to be at 6. 2, it's going to be at 4. 3, it's going to be at 2. And then 4, this is really what we need to see, it's at 0. And we could continue that pattern. Again, here our velocity function is linear. And again, this supports what we're seeing with this motion of a particle along a horizontal line. It starts with a positive velocity. So it's moving in the positive direction. And at the moment where this linear function crosses the x-axis, we can think that the velocity is 0. And that would correspond to this moment right here when the particle stops and turns around. And then when the velocity dips below the x-axis, it's becoming negative, and so it's headed in the left direction. So again, the velocity function gives us information about the nature of this particle's motion. We can go ahead and graph our final piece here, which is acceleration, and it's at -2. Very easy to graph that constant function. And basically what that's saying is that for this particle, it's in fact slowing down constantly until it's turning directions and becoming larger and larger and larger in the negative direction. Well, that completes the graphing portion of the task. So we've come up with something for the velocity function, part A, acceleration function, part B, and part D, we've graphed the 3 functions. So position, velocity, acceleration. And all that's left is for us to complete this part C, where we find the times when the particle changes directions. And then the intervals of time when the particle is moving left and moving right. Well, we've actually already found that. So we saw here on our horizontal green line that would represent the motion of this particle, that the particle moves up to a position of 81. And we established that that's right here at the vertex of the quadratic. It's also represented by the x-intercept of the linear velocity function. That's time equals 4 seconds. And that's when we see a change in direction. We can then also complete this second part, the description of the intervals of the time when the particle is moving left and moving right. So the particle is moving to the right when it's got a positive velocity. And so that's really from 0 seconds up to 4 seconds. And we can record that particle moves right when the velocity is positive. So again, that would be from 0 is less than or equal to time is less than or equal to 4 seconds. And to finish this out, to say when the particle is moving to the left, that is when the velocity of this function is negative. It's moving to the opposite direction from its rightward initial movement. So it's moving to the left from 4 seconds to, if possible, infinity, if we let that particle move forever. And it would be moving to the left forever because our velocity function, which again is related to the position, is negative once it crosses the x-axis at 4. Well, thank you for joining for this investigation of rectilinear motion and finding velocity and acceleration functions when I'm given a position function. See you soon.